They called it the graveyard of the modern age. 1 billion tires, forgotten and left to rot. Indestructible, non-biodegradable. For decades, we thought this was the end of the road. But where others saw an environmental disaster, human engineering saw an untapped gold mine. It starts with the harvest. To create millions of gallons of fuel, the beast must be fed. 24 hours a day, 7 days a week. The intake never, ever stops. Millions of tons of rubber embark on a journey of resurrection.
Every single piece must be processed.
At this scale, there is absolutely no room for error.
Into the belly of the machine they go, ready to be stripped, crushed, and broken.
Make no mistake, this isn't traditional recycling. This is brutal chemical deconstruction. Before the tires can be converted into fuel, they must be utterly destroyed.
These are engineered for extreme highway survival. The vulcanized rubber and woven steel are meant to be indestructible. The chunks are fed into the primary shredders. Here, massive intermeshing steel gears chew the rubber into smaller blocks. It's an incredibly violent process that generates immense friction and deafening industrial noise.
But rubber is only part of the anatomy. Up to 20% of a heavy-duty tire is made of woven steel wire.
As the torn chunks pass beneath a massive industrial electromagnet, the machine acts like a tractor beam.
It violently pulls the razor-sharp wires out of the rubber. In this mega-factory, absolutely nothing goes to waste.
This steel is collected, compacted, and sold directly back to foundries to be forged into new products.
Now completely freed of steel, the rubber goes through a final, high-speed granulator.
It is repeatedly milled and crushed until it becomes a fine, uniform aggregate, known as crumb rubber.
This dramatic reduction in size is absolutely crucial. By turning blocks into tiny pellets, they drastically increase the surface area.
This ensures a highly efficient, perfectly even chemical reaction in the next, most extreme stage of the factory. We now enter the beating heart of the facility. The environment here is hot,
Pyrolysis is the secret to this entire operation. It is a thermochemical decomposition of
Once full, the heavy steel vault doors are hermetically sealed and locked tight. Once full, the heavy steel vault doors are hermetically sealed and locked tight. If even a fraction of oxygen were present beneath the rotating drums, massive industrial burners roar to life. The temperature inside the reactor climbs rapidly,
pushing past 400 degrees Celsius, or roughly 750 degrees Fahrenheit. Inside the dark chamber, the solid rubber pellets begin to sweat,
then melt, turning into a bubbling, boiling, viscous black tar. But the heat keeps rising.
At these extreme temperatures, the long, complex polymer chains that make up the rubber simply snap.
Factory engineers monitor the internal pressure and temperature curves relentlessly. A rupture here would be catastrophic.
In glass control rooms, their eyes are locked on walls of glowing monitors. Every second is a high-stakes balancing act.
They manage the pressure. If it builds up too fast, the system could fail. If the temperature is too low, the oil yield drops.
Reactor through 3. Watch that pressure spike. Standard release initiated.
The reactor has done its job. The tires have been vaporized. Now, that superheated hydrocarbon is finalized. The ancient rubber has been reborn as an invisible, powerful force, rushing toward its cooling destiny.
This matrix is a sprawling, complex labyrinth that looks like the engine room of a massive spaceship.
Here, the extreme heat of the gas meets sudden, plunging cold. High-capacity pumps circulate chilled water around the pipes.
Here, the extreme heat of the gas meets sudden, plunging cold. High-capacity pumps circulate chilled water around the pipes.
As the hot, pressurized gas rushes through the system and hits the chilled walls, physics takes over. The physical state of the material shifts instantly. The gas undergoes rapid condensation,
Turning from a white-hot vapor into heavy, dark droplets. Slowly at first, and then in a massive, rushing stream. The extreme temperature drop forces every last hydrocarbon molecule to return to a liquid state.
The tire has completed its journey backward through time. What was once a solid wheel rolling on asphalt.
At this stage, the oil is crude and unrefined. It holds incredible energy density, but it is thick with impurities. To make this product market-ready, it must be purified. The crude oil is pumped into advanced centrifugal separators, while further chemical treatments strip away the excess sulfur and trapped moisture.
Inside, the oil is spun at blinding speeds. Gravitational force pushes the heavy particulates to the outer edges,
while further chemical treatments strip away the excess sulfur and trapped moisture,
leaving behind a highly potent, refined black fuel oil. The surface is perfectly smooth, reflecting the lights like a dark mirror.
Its calorific value is incredibly high, tested and proven to directly rival that of standard commercial diesel.
While this heavy fuel is too dense for your average consumer car, it is the absolute perfect, cost-effective powerhouse fuel for heavy industry.
It is eagerly purchased to fire up massive cement kilns, run giant steel mills, and power the global machinery of the modern world.
With the oil refined and rigorously tested, a fully automated packaging line springs into action to supply commercial buyers.
High-speed robotics effortlessly hoist and stack these heavy drums, shrink-wrapping them for global export.
But the vast majority of this factory's output leaves by the megaton. Powerful pumps fill these rolling leviathans in minutes.
Dispatched across the continent, this recycled energy is injected directly into the arteries of heavy industry, keeping our modern world moving. What started as an apocalyptic mountain of toxic waste has been reversed. Millions of discarded tires are saved from the landfill.
This is the power of pyrolysis. The fascinating alchemy